to find KSP if you have the concentration of a saturated solution. You find the ion concentrations, you write the solubility equilibrium equation, and you write the KSP. Okay, when in doubt, these three things apply to most situations involving a KSP. Not all of them, not all the time. Sometimes there's little differences, but most of the time those three things will get you somewhere near where you want to go. So in terms of our ion concentrations, what is the concentration of barium? Yeah, 0.1091 molar. I'm not going to write the whole thing again. And what about the concentration of hydroxide? Tell your partner what you would have to do to find the concentration of hydroxide. Well, we've got this little 2 down here, yes? So we would need to multiply 2 times 0.1091, which would give us 0.21825. There we go. Solubility equilibrium equation. BaOH2 in equilibrium with Ba2 plus 2 OH minus. That's mainly just for getting your points, right? Getting your half mark for writing that. KSP is barium times hydroxide squared, which is barium times 0.21825 squared times 0.1091 gives us 5.2 times 10 to the negative 3. There's a reason that one is a challenge, yes? Because you had to think 2 ways about it. You had to think, oh, first of all, I've got this precipitation reaction, and that's like a titration. Then I have to do some KSP stuff. Is good? Okay. 3.2C, number 3 and 5. 3.2C. Number 3 and 5. We want to know if a precipitate will form. We have 25 mils of 0.0020 molar, and that is our PB NO3 2. And we have NABR 25 milliliters times 0.040 molar, and we want to know, will it precipitate form? And this is 3.2C number 3. First of all, who would be the precipitate? Yeah. Are we happy with what I've written? It has to be PBBr2 because we've got that 2 there, right? And NO3 each have a charge of negative, so the lead that goes with them must be 2 positive. Okay, and the bromide is negative, so that's why we have that there. If it is a will precipitate form, what tool are we going to use? We're going to use a Q. So we will need to write our solubility equilibrium expression, and we will need to write a Q. So the solubility equilibrium expression is going to be for the precipitate. You're not writing it for lead nitrate or sodium bromide, you are writing it for lead bromide. And the Q is going to be concentration of lead times the concentration of bromide squared. Can I just do the following? Can I take this number and plug it in there into my Q? Why not? Chat with your partner about that one. Why can I not just take this number here and plug it in there? That's just not going to work, but why not? Okay? Yes, those two solutions get mixed and they dilute one another. Okay? So we cannot do this. We need to find our diluted concentrations before we plug into the SEE. So I'm going to get rid of that. And so now we want the concentration of lead diluted, which is going to be the same as the concentration of Pb NO32, because there's one lead in one lead nitrate. And that is going to be our old concentration times our old volume, 25 milliliters, over our new volume, which is going to be 25 and 25 is 50. If you like solving for your dilution some other way, that's perfectly good. This is my preferred method, but you can use anything you choose. And we get 0.0010 molar Pb2+. The concentration of bromide. Bromide is coming from sodium bromide. How many bromides are in sodium bromide? Just the one. So that's also going to be equal to the concentration of sodium bromide diluted. Diluted. 0.040 molar times original volume over our new volume. That gives us 0.020 molar bromide. I'm going to put red boxes around those so I can find them easily, because now I want to take those concentrations and plug them into my Q expression. So the lead is 0.0010 and the bromide is 0.020 squared. 0.001 times 0.02 squared is 4 times 10 to the negative 7. That's our Q. What do we do with the Q? Compare it to KSP. Let's go check what KSP says for lead bromide. 6.6 times 10 to the negative 6. Excellent. Ooh, that's like a demonic kind of KSP, isn't it? Sorry, I'm just being very silly. So that is compared to KSP, which is 6.6 times 10 to the negative 6 And it is that bigger or smaller? Smaller than KSP. Therefore, no precipitate will form, or a precipitate will not form, okay? Okie dokie. That was number 3. Let's grab number 5. Ooh, 5 is a little icky, yes, because it's got that weird polyatomic ion, 50 mils, 4.5 times 10 to the negative 6. So we've got 50 mils, whoops, of 4.5 times 10 to the minus 6 molar, and that is our Hg2 NO32? NO32. Our other substance is 25 mils, 2.5 times 10 to the minus 6. 25 mils, 2.5 times 10 to the minus 6 molar, and that was barium chloride. Barium chloride, barium chloride. And the KSP of Hg2Cl2, 1.3 times 10 to the negative 18. 1.3 times 10 to the negative 18 is the KSP of Hg2Cl2. Okay, that's really bad. Move that over. SP of Hg2Cl2 is that. So, once again, we need to identify who is the precipitate. Well, the nice thing is that if they give you a KSP, you know that that has to be the precipitate. That just looks so weird. There we go. No, I don't know. Anyway, our precipitate is Hg2Cl2. So we need, once again, we need our ion concentrations. We need our SEE. And in this case, we're going to use a Q instead of a KSP. Concentration of Hg22 plus. Hg22 plus is just a polyatomic ion like every other polyatomic ion. It just looks a little weird, yes? But we can calculate its concentration because it's going to be the same as Hg2, NO3, 2, and these are all diluted, diluted, diluted. 4.5 times 10 to the negative 6 molar is the original concentration, times our old volume, 50 mils, over our new volume, 25 mils. Yes, of course. 4.5 times 10 to the minus 6 times 50. Oh, that shouldn't be 25. That should be 75. 75 divided by 75 is 3 times 10 to the negative 6 molar Hg2 2 plus. Concentration of Cl minus. Now, is it equal to the concentration of barium chloride? Is that a true statement? No, because we have this little 2 down here, the chloride ion concentration is going to be twice as much. If barium chloride is 1, chloride will be 2. If barium chloride was 2, chloride would be 4. Okay, so we're going to have to double it. So I'm just going to put right out at the front 2 times, and then I'm going to do everything else. We have 2.5 times 10 to the negative 6 molar times 25 mils over 75 mils, which is equal to, let's see, 2 times 2.5 E6 negative times 25 divided by 75 is 1.67 times 10 to the negative 6 molar chloride. And now we write our solubility equilibrium equation for Hg2Cl2. When that dissociates, remember Hg2, 2 plus, is a polyatomic ion, so it stays together. Strange little critter though it is. But the chloride is not a polyatomic ion, so it just behaves normally. We end up with 2 Cl minuses. KSP, or Q rather. Q is Hg2, 2 plus, times Cl minus squared, which gives us, oh, let's see, what was our Hg? That was 3 times 10 to the negative 6. 3 times 10 to the negative 6 molar. And the chloride was 1.67 times 10 to the negative 6 molar. And we want to square that. .3 times 10 to the negative 18. And this weird little compound is not on our table of KSPs because it's not a common one, and our table only has the most common ones. So we have to go back up to our question and see that it's 1.3 times 10 to the negative 18. 1.3 times 10 to the negative 18 is our KSP. And we get, well, let's see. Ooh, it's bigger. And if Q is bigger than KSP, a precipitate will form. Do you guys want me to keep going? Or are you tired of listening to me? No? You want me to keep going? No, you don't. You're tired of listening to me. I understand. I would be tired of listening to me. It's been like, I don't know, a long time. Shall I pause? Do you want, are there any questions from here that people are like, no, please tell me? I can keep going and you can just ignore me if you don't want. Shall we do 3.2D number 4? Yes? Okay, we'll do 3.2D number 4. I'll just keep asking the same thing. You can just ignore me and continue working on other things. Okay? 3.2D number 4. Oh, it's all our challenge questions. Okay. How many grams? So this is 3.2D number 4, and we want to know how many grams of MgOH2 needed to completely saturate 1.5 liters of the solution. If we are completely saturating that solution, the concentration of MgOH2 will be saturated, and that is the same as the solubility. We can find our grams because we've got the volume. We can find the grams as long as we know the concentration. So the first thing will be to find the concentration. So we will say let X be the solubility of MgOH2. So there's our let statement. Let's do the solubility equilibrium equation. MgOH2, solid in equilibrium with Mg2 plus aqueous plus 2, OH minus aqueous. And then we're going to put in our X's. Okay, so our concentrations are X. There's no coefficient in front of Mg, so it is just X. And there's a coefficient of 2 in front of hydroxide, so that is 2X. KSP, concentration of magnesium times concentration of hydroxide squared, X times 2X all squared, X times 2X all squared is 4X squared. And if we multiply X, we get 4X cubed. And let's check and see if it gave us a KSP or if we need to look up that value. I see no KSP, so we need to look up that value for magnesium hydroxide. 5.6 times 10 to the negative 12. So we have 5.6 times 10 to the negative 12. So X cubed will be 5.6 times 10 to the negative 12 divided by 4. (1.4) times 10 to the negative 12. And now we'll take the cube root of that, everything, and we'll get X is equal to, where's my cube root on this calculator? Do I have one? I do, how nice. And we get 1.112 times 10 to the negative 4, and that is molar, and that is the concentration of MgOH2 saturated, because that is our solubility. Whew. But we don't just want to know the concentration. The question says, how many grams do we need to saturate 1.5 liters? So the grams of MgOH2, we're going to start with our 1.5 liters because we can convert liters into moles by using the molarity, the moles per liter. 1.112 moles per liter times 1.5. Okay. And then, oh, we need our molar mass for MgOH2. And MgOH2 is, let's see, 24.3 plus 16 times 2 plus 2 is 58.3 grams of MgOH2 per mole times 1.112 E4 negative, oops, times 10 to the negative 4 times 1.5 gives us 9.7 times 10 to the negative 3 grams of magnesium hydroxide. Is good? Okay. (3.2G) number 5. Do we want to do that one? Yes? Okay, we'll keep doing it. Okay. 3.2G number 5. Okay, so this is a titration. And we have here 25 milliliters of well water is titrated with 0.1 molar AgNO3. And I'm going to highlight in yellow my AgNO3 because my volume of AgNO3 is here. The well water has been titrated to figure out the concentration of chloride in the well water. So we know the volume of the chloride. So for chloride, we know that it is 25.0 milliliters. For the silver, and you can either call this silver or silver nitrate, it doesn't matter. Either way is fine. We know we have 0.100 molar. But in any titration, you always need one of the two substances where you know both things, the volume and the molarity. So we're going to have to use this data here to calculate the volume of silver or silver nitrate. Can we just use all of those data? Or is there an outlier? These values here are all within 0.2 mils of each other. However, this is at least a milliliter off, more than 1 milliliter away. So that means that when we take our average, we have to leave this out of the average. It is an outlier. So, averaging. You would not believe the number of people, grade 12, you guys are all taking like pre-cal 12 and stuff, how many people said to me, how do I take an average? It's because there's too many things in your brain. Some of the easier ones that you've learned before have sort of trickled out your ear because they've been displaced by so much other stuff. Simple, just do what you did like back in, I don't know, when do you learn averages? Grade 5. Yeah, do your grade 5 math here. We're going to take our 3 data points, Do you need to show this work? Yes, you do. Plus 17.91. Oh, I should do this over underneath silver. 17.86 plus 17.91 plus 17.88. And then because I've got 3 of them, I divide by 3. And we get 17.86 plus 17.91 plus 17.88 equals, divide by 3 equals 17.88, and I'm going to keep an extra digit, 3 milliliters. Okay? So in a titration, we're going to go from our known substance to our unknown substance. And we call this the unknown substance because we don't know its molarity. We call this one known because we don't know both the molarity and the volume. This one I'm going to show in a single line. So let's calculate the concentration of chloride. But we're going to start with the volume of silver. 17.883 milliliters. I'll show the work another way in just a moment, but this sort of simplifies things if you like it. Times 0.100 moles per liter, and that's moles of silver. Whenever you're doing a titration calculation, it's important that you write who you have moles of because you'll be changing from one to the other. Times, oops, I need a balanced equation. 2 ways of writing that balanced equation. You can either have silver plus chloride gives silver chloride. And remember, in a titration, we always use the precipitation reaction, precipitation equation, the PE. So we have our one-way arrow, and we have our solid on the right. You could write it this way, or you're also welcome, if you wish to write it like this, sort of a mix and match. It's neither formula equation nor net ionic equation. Either way, you end up with a 1-to-1 ratio between the silver and the chloride. So when we go to find our moles of chloride and cancel out our moles of silver, it's a 1-to-1 relationship. And if anyone's feeling a little weird about this milli here, don't worry, I'm going to show the work a different way in a moment, so you don't have to worry about that. But let's just look at how things cancel. Liters cancel with liters. Moles of silvers cancel with moles of silver. We want the concentration of Cl-, which is the moles of chloride per liter of chloride. So right now we have moles of chloride, but we need to have liters of chloride down on the bottom, and we're just going to put a 1 on the top because that way it still works. Okay, I don't want to mess around with my top part because I have what I want on the top. Volume of chloride, 25 milliliters. 25, milliliters. And remember I said I could worry about those millis later? I got milli here and milli here. If I do it all in one line, I don't actually have to convert my millis because they cancel out. And all I am left with now is moles of chloride per liter. 17.883 times 0.1 divided by 25 is 0.07153. And let's see what our volumes were. Oh, three sig figs. 0.0715 molar Cl minus. If you find the work all in one line to be too confusing, yes, of course, you can, instead of doing it all in one line, you can say, I'm going to find my moles of chloride, and I'll actually turn my milliliters into liters, 0.01788 liters times 0.100 moles of silver per liter times 1 mole chloride per 1 mole Ag plus, and we get 0.001788 moles of chloride, and then you can find your concentration of chloride in a separate step, 0.001788 moles divided by 0.02500 liters, and we should get the same answer, 0.0715 molar chloride. Whew. So much of me talking today. Have you gotten good at ignoring me? All right. What was our last one? 3.2i, number 7. Oh, where'd you go? 777. There we are. Oh, I like this one. Because actually, I did want to talk about this with everybody. You can, the actual experimental procedure for finding solubility, yes, or finding the KSP, you actually have to make a saturated solution first. How would you make a saturated solution of magnesium fluoride? You would add it, and you would stir it, and you would add it, and you would stir it until no more will dissolve. Now, if you want to know the concentration of that saturated solution, you can take a measured volume and evaporate the liquid to leave the solid behind. Are you with me so far? So we've evaporated the liquid and we've left the solid behind. The only problem with that is that we need to make sure that the sample that we're taking doesn't have any of that solid that did not dissolve. Otherwise, you'll have both solid that didn't dissolve and solid that did dissolve. So the procedure for something like this would be, number 1, use the dump and stir method. To make a saturated solution of MgF2. You would probably write out what the dump and stir method is, but I'm just writing that to be quick about it. Second thing, you will filter out any undissolved MgF2. If you measure out a specific volume of the MgF2, that will give you liters. Yes? And what else are you going to need to have the solubility? You're going to need moles per liter. So you can then evaporate this to dryness, and measure the mass of the solid left behind. And that's going to be grams. Oh, guess what? Now you've got grams per liter. You could convert that to moles per liter if you needed to. Now you have a solubility in moles per liter, and you could find your KSP. Now, it's a little more complicated than that, because when you go to evaporate it, it's not like you can just put it on the scale and let it evaporate. You're going to want to heat it. And in order to heat it, you'll need a container, yes? So let's say you have it in a beaker. Once it is heated and the salt is left behind, the salt will all be crusted on the sides of the beaker. So how are you going to know the mass of the salt if it's stuck to the beaker? Yes? Of a similar beaker, did you say? No, beakers weigh different masses. But you're close. What did you do? But you have to do it beforehand. You will measure the mass of that actual beaker ahead of time. Yes? So somewhere up in here, you're going to measure the mass of a beaker. Yes? Then when you measure out your specific volume of MgF2, you will place it in the beaker. Does that make sense? So now you know the mass of the beaker, you've placed that in there, you're going to evaporate it to dryness, and now you're going to measure the mass of the beaker and the, oh, hang on. Measure the mass of the solid left behind plus the beaker. And then step 5 is going to be to subtract the mass of the beaker. To find grams of solid. So that is what is happening in this question. So in this question, they didn't use a beaker, they used an evaporating dish, but they had the mass of the evaporating dish before, and they have the mass of the evaporating dish and the MgF2. What are you going to have to calculate from these two things? Yes? you're going to have to calculate the mass of the MgF2. So for this one, mass of MgF2 is equal to mass of evaporating dish plus MgF2 minus the mass of the evaporating dish. So that would be 78.5434 grams minus 78.5418 grams. And you'll notice that difference is not a whole lot. So if you were to have used a different beaker, that would make your results extremely different, because probably the mass of the beaker is bigger than that difference in the difference in the mass of the beaker is probably bigger than that difference. I don't know what I'm saying, but you kind of get it, okay? Yeah. Okay. 0.0034 minus 0.0018 is 1.6 times 10 to the negative 3 grams, or you could write it as 0.0016 grams. Now that we know that, we also know the volume. Yes? So now we can find the concentration of MgF2, 0.0016 grams per 0.100 liters, because we know it is in 100 milliliters. Oh, by the way, did you notice what happened to my sig figs when I did the subtraction? I went from having like 1,000,000 sig figs to having only 2. Yes? Because when we subtract, it goes to our first uncertain digit, which is that one there. So even though I've got 100 milliliters to like 1,000,000,000 digits, it really doesn't matter. Divide by 0.1 is 0.016 molar. If you know the concentration of MgF2, can you find the KSP? Or do you want me to go through that part? Yes or no? Yes, you would like me to? Okay. So, I know the concentration of MgF2. Remember, we want to find our KSP. We're going to need our ion concentrations. We're going to need our solubility equilibrium expression, and we are going to need our KSP. What's the concentration of magnesium? Is it the same as MgF2? Yes, 0.016. How about the concentration of F? Is it the same? It's going to be 2 times that. So 2 times 0.016. Oops, I should put molar there. So that's going to be 0.032 molar. Our solubility equilibrium equation. And our KSP. (1.6 times 10 to the minus 5). And we are done. Yay? Yes. Did we not convert to moles? I thought we did that. Oh, shoot. Hold No, we didn't. Oh my God. Look at that. Miss Spence losing marks all over the place. This is grams per liter. We would have to convert that to moles per liter first, and then do the ion concentrations. But we're out of time for today, so you can just pretend that we did that step. Okay? Woo!